Okay. So, we have already discussed about the STFT analysis. Okay. So, STFT, now we discuss about the STFT synthesis. Okay. So, in STFT analysis, what we have done that I have a long speech signal. We have taken one segment of the speech signal, and for that segment we have done that STFT of that segments of speech signal. Now, if you see that in normal Fourier transform, if xn is my signal, if I apply discrete Fourier transform on xn, I will get xk. Once I apply the IDFT in here, I should get back xn. So, this is the normal Fourier transform property. Okay. Now, STFT also follow the normal Fourier transform property. So, I can say okay, I have done STFT, can I get back the signal again? It is possible. So, what we want to hear, the suppose something analysis I want to do in you can say the frequency domain, and then again I want to get back the time domain signal. So, what do you want? Suppose I have a speech signal and I want some processing in frequency domain, some enhancement, we have to enhance some frequency band of this signal, okay. And then again I want to get back the speech signal. Since we have not taken the whole speech signal at a time, we have taken part of a speech signal, then what we have done, we have taken that if you remember the example, suppose I have a 16 kilohertz sample signal, I have recorded 3 seconds of my speech, then I have 4800 sample in 3 seconds. So, I have not taken all sample at a time and done that STFT analysis or done the Fourier transform, then it is very easy. I take whole signal at a time and done the Fourier transform and get back the signal. Since the speech is non-stationary signal, this is true for stationary signal. Speech is a non-stationary signal, that means along the time speech signal changes its property. Okay. So, what we do, we instead of analyze whole signal at a time, we take a small segment. Okay. So, if I take a 20 millisecond window, then I get 160 sample, 320 sample. So, if I do the STFT analysis using Fourier transform, so nearest 2 to the power something which is 256, 512 point DFT I have applied, n equal to 512 point DFT. So, I have padded up a 0, 320 sample plus some 0 to get 512 sample. So, once I done the reverse transform, I will get a signal which is not exactly 320 sample, it is something 212 sample, and also since it is not the, you can say I cannot get back the xn itself, because that I have multiplied that signal with a window function. So, it is a multiplication of window function and the signal. So, my intention is that if I want to do STFT synthesis, I have to get back the xn exactly. So, in mathematics, how do you get back? Okay. Let us do the STFT synthesis in mathematics. So, what I have done, for a given value of, I have done STFT for time instant n, this is my STFT output signal. Okay. So, it has the property of Fourier transform, so inverse transform is possible. Okay. So, if I have get frequency transform of what? Signal plus window. See, if I take the IDFT in here, or so this is DTFT, IDTFT in here in digital domain, or if it is in DTFT, discrete time Fourier transform. If it is in DFT, then it is n k, this is DFT. So, if I take the IDFT, I will get back xn multiplied by omega n minus n, because I have taken the frequency transform of this signal only, xn multiplied by the omega n minus 1. So, I can say what I obtained Fm, which is nothing but a xn, or you can say if it is I write m, then it is m, this is n minus m. Okay. So, I have get back the signal which is multiplication of xm and omega n minus m, not xn directly. So, if I want to get back the xm, so xm, small xm is nothing but a fm, whatever I get back divided by omega n minus m. Okay. Now, if I evaluate fm, or for every m equal to n, so if m equal to n, then x of m is nothing but a fm divided by w 0. Okay. So, if w 0 is not 0, then only I can say I can get back the signal. So, if w 0 is non-zero, then only I get back the signal. Okay. So, which is already explained if you see in here this slide. So, I have taken a, this is my fnm is my framed signal, which is nothing but a xm multiplied by the window function. I take the DFT and then I take the IDFT and evaluated at m equal to n, I get xm multiplied by omega 0. So, xn is nothing but a inverse Fourier transform of frequency domain representation of STFT with 1 by 2 pi into W 0. So, this is a synthesis equation of STFT analysis. Okay. Now, what is the problem in here? So, for every m is equal to n, I have to evaluate it. Okay. So, suppose, so there is a two case is there. Suppose I have a signal. So, I can say the xm is recovery is possible in two conditions. One is that I have to know sample by sample recovery process at for every m equal to n, I have to do the recovery process. So, for every sample by sample recovery process I have to done, and I have to know x of n omega for every omega value. So, I can say that complete recovery is possible if sample by sample recovery process is done and x of n omega must be known for all omega. So, suppose I have a long signal and I do STFT, then what is required that for every sample, so I have taken a some portion of the signal and for every sample I have to recover it. So, suppose I have a 4800 sample point, then synthesis is possible if I shifted the window, analysis window for every sample, which is computationally not feasible, because FFT calculation is a time consuming matter, lot of complexity is there. So, if I want to sample by sample recovery, that is not a possible solution. Second one is that I have to know x n omega for every omega. So, what kind of things I should allow, or what limitation is, what kind of shifting is allowed, so that yes, it is complete recovery is also possible and I have not processed sample by sample. So, those are two things we have to analyze. So, let us case 1. What is the case 1? Case 1 is that suppose I have a signal, I have done that STFT of a signal of nth window, which is nothing but a xn omega. Okay. So, I have taken the DFT, length of the DFT, n is equal to the length of DFT length is equal to n. So, what we have done, that whole frequency scale 0 to 2 pi is the highest frequency. I have divided 2 pi by n resolution. So, I can say whole frequency scale can be think about a some filter. This is 0, this is 2 pi by n, this is 2 pi by n into 2, this is 2 pi by n into 3. So, that way. Okay. Now, if I say this is the number of DFT, if DFT length is equal to n, that I can say whole frequency scale is divided into n number of channel or n number of filter, n number of filter or n number of channel. Okay. Now, I have, when I do the STFT, I multiply the signal with a window function, So, the bandwidth of the window is B. Bandwidth of the window means I take the frequency response of the window and find out the bandwidth of the window is B. Now, in STFT analysis, what is happened? The frequency response of the window function is convolved with the original frequency response of the signal. So, I can say the frequency response of the window function, if the bandwidth is B, so there will be a B at every 2 pi by n modulation, as we already explained in DFT filter view. Now, if I say if this is my bandwidth, so distance between these two is 2 pi by n. If the bandwidth is less than the 2 pi by n, so if the 2 pi by n is greater than B, okay, so that means that there is a gap between the two filters. This is the gap. If there is a gap, so this portion of frequency is not passed through the filter. So, if it is this portion is not passed to the filter, then I cannot say the x of n omega is known for all omega. So, since there is a spectral loss, so complete recovery of xn is not possible due to the spectral loss. So, what will be the optimum condition? At least 2 pi by n must be equal to the bandwidth. 2 pi by n must be equal to the bandwidth, or I can say B must be greater than equal to 2 pi by n. If it is there, then I can say none of the omega is left out, all omega is pass. Okay. So, if it is B equal to 2 pi by n, then the picture will be, what will be the pictures? So, pictures will be, if this is my 2 pi, so this is B, again there will be a B, so this is B, again there will be 2 pi, there will be a B in here. So, I can say if the bandwidth is B, then all frequency, so this gap is not there, that is why I know xn of omega for all omega. Okay. So, there is the one limitation. Second limitation is that I have said the sample by sample recovery. So, I have shifted the window one sample, which may not be necessary. Only thing is that consider x and a band, the dissemination factor is L. So, STFT is applied for every L sample. So, x of W of n is non-zero over the NW, NW is the length of the window. Then, if L is greater than NW, so there are L is greater than NW. What is the case? Let us consider these slides. If you consider these slides, so this is a triangular window, triangle. So, triangular window, length of the, okay, I just explained in board also because of the slides is. So, suppose I have a signal, okay. So, I said STFT complete recovery if I shifted the signal by one sample, okay. So, for every one sample it is okay. Now, I said let us I shifted the window, dissemination factor is L. So, this is my window, okay. So, the length of the window here to here, length of the window is NW. If my dissemination factor means shifting of the window is greater than the NW, L is greater than the NW, so next window may be come in here. So, L I have shifted the window in here. So, next window come in here. So, what has happened for this portion of signal? I do not know. I do not know this portion of the signal. So, complete recovery is not possible. So, it is complete recovery is possible, at least L should be less than NW. Okay. So, if you see in the red color I have written Xn is invertible if the temporal dissemination factor L is equal to or less than the size of the analysis window. So, it should be at least L should be at least equal to L should be NW analyzed window length, or L must be less than to NW. This is one condition. Second condition is that 2 pi by n must be either equal to B or greater than equal to B. B must be greater than the 2 pi by n. So, number of channel if it is n. So, distance between the two channel is 2 pi by n. This must be less than the bandwidth of the analysis window. So, there is a two condition is there. STFT is completely invertible if L is less than equal to NW. So, length or I can say dissemination of time or shifting of the window is less than the length of the analysis window, and the number of channel if it is n, then the distance between the two channel, which is 2 pi by n, must be less than equal to the bandwidth of the analysis window. So, this is the two condition is there. Using this, if this two condition is satisfied, then it is completely invertible process. So, STFT synthesis is possible only for these two cases, and there is a two procedure for STFT synthesis. One is called filter bank summation method, another is called overlap add method. So, in this you can say in this lectures this course I will discuss about the two methods. One is called filter bank summation method, another is called overlap add method. So, let us go one by one. So, if you see filter bank summation method, I am not. So, traditional short time synthesis method is a commonly referred as a filter bank summation method. Okay. So, FBS is best described in terms of filtering interpretation of the discrete STFT. So, if you remember this STFT analysis block diagram, what we does, we pass the signal through the window, then we modulate the signal, or you can say demodulate the signal or shifted the signal e to the power minus j 2 pi by n by 0. So, this is the synthesis equation, this is the synthesis block portion. Now, if I want to analyze this thing, so if I done demodulation, I have to done again for every x n omega 0, I have to modulate it and take it sum, and I get back the 1 by n into omega 0 w 0, I get back the signal y n. So, y n is equal to x n if w 0 not equal to 0. So, that is the synthesis equation. So, this is FBS method STFT synthesis. Let us go to the details maths, what is there. Okay. So, in FBS method, if I want to, this is my frequency domain representation of nth window is x of nk. X of nk is my frequency domain representation of nth window. Okay. Now, if I take the IDFT, I get the time domain signal. So, let us time domain signal is yn, then yn is equal to inverse Fourier transform of x nk. So, I can say 1 by n, or I can say yn. So, in inverse Fourier transform, what should I get? Instead of yn, I can write yn w n minus m, I will return back. Okay. So, instead of that, I can say it is written that yn I have written, and here I write w 0. That completely recover if the w 0 is not 0. So, I say w 0 I have write here. So, 1 by n is the normalization factor into w 0 inverse Fourier transform, inverse DFT k equal to 0 to n minus 1, length of the DFT, x of nk into e to the power j 2 pi by n into nk, inverse IDFT. So, this is the IDFT. Okay. So, what is x nk? X nk is nothing but a Fourier transform, which is m equal to minus infinity to infinity x of m w n minus m e to the power minus j 2 pi by n into nk or km. So, if I replace this thing in here as it is here, I can replace it. Now, if I interchange the summation operation, this equation reduced to 1 by n w 0 x of n convolution with k equal to 0 to n minus 1 w n e to the power j 2 pi by n k. So, I can write, after putting this value, I can write w y n is equal to 1 by n w 0, okay, w 0 x of n convolved with k equal to 0 to n minus 1 w n e to the power j 2 pi by n into n k. Okay. If it is that, then I can say what is this? I can change this Wn, I can get back in here. So, I can say 1 by n W0 into x of n, convert this Wn outside and put that k equal to 0 to n minus 1 e to the power j 2 pi by n nk. So, what is this? Finite sum over the complex exponential, finite sum over the complex exponential. So, that reduced to is nothing but a impulse strength with period n. So, it is nothing but a impulse strength with period n. Then I can write 1 by n into W0 is equal to xn convolved with Wn into, I can say, let us r equal to infinity minus infinity to infinity, infinite sum del function of r minus n minus r into n, period is n, r multiplied by n. So, r equal to infinite sum, okay, with period n, impulse 10 with period n. So, this is the impulse 10 with a period n. So, I can say yn is the output of the convolution xn, this is the constant. So, I can say yn is the output of the convolution of xn with a product of analysis window and impulse strength. So, ultimately yn is nothing but a xn convolved with window function, product of window function and impulse strength. So, what is the meaning? Product of window function and impulse strength. Okay. So, I can say Wn into r equal to infinity minus infinity to infinity del of n minus Rn, this is equal to delta n if this is equal to delta n if window length Nw is less than equal to the analysis length and this is true because if I want yn should be xn, then this must be W0. So, W0 means delta n. So, this if it is W0, then W0 will be cancelled, then I can say yn is equal to xn, or I can say this, if I say this is equal to Wn into W0, then I can say this replaced by Wn, W0, W0 cancel, then I get it. Okay or not? So, I can say this function, this Wn product of W window, analysis window and impulse strength must be delta n if Nw is less than equal to n, Nw is less than equal to the the length of the DFT. So, what is the physically meaning? So, Wn is 1. Okay. So, this must be less than the analysis window because it is product of R into N. Okay. So, in that case, this is the single case. Second case, if Nw is greater than equal to N or is greater than N. So, another thing is Nw is greater than N, then also it is possible, but if Wrn is equal to 0 for r not equal to 0. That means WRN equal to 0 for all r except 0, which is r equal to minus 1 1, because it is minus infinity to infinity, minus 1 1, minus 2 2, minus 3 3. Okay. So number 1, it is straightforward delta n if it is NW is less than the n. Second one, even if NW is greater than n, then I have to ensure that WR into n is the length of the analysis window, must be 0 for all r except r equal to 0. Okay. So if I take this, let's instead of time domain, if I take the, so this is the constraint of FBS analysis. So if I take the frequency analysis of this, then what I will get, k equal to 0 to n minus 1, which is nothing but a W. So this is W, capital W, omega minus 2 pi by n into k is equal to delta n, nothing but a n into W0. Okay or not? Okay. So this, if it is this, then satisfy this condition. Okay. Then if I see this, what is state that? This is nothing but a constant. W0 is not 0. Summation of all frequency component. If I take the expression state, the frequency response of the analysis filter should sum to a constant across the entire bandwidth. Okay. So this state that the frequency response of the analysis filter should sum to a constant across the entire bandwidth. This is constant, is equal to constant. So the summation of all frequency response of analysis filter must be a constant. So next class I will describe the pictographically this one. Okay. Thank you.